Hi, my name is Peter Wilder. I am an HVACR application engineer at ABB. Today I'd like to discuss with you the use of Intelligent Process Control, or IPC, on the ACH 580 drive. What I want to specifically discuss is how we can set up the ACH 580 drive in a basic speed follower mode and get automatic system redundancy by enabling IPC on the VFD. We're going to start out this presentation by first discussing the traditional implementation of IPC and what that looks like and how it works. We're then going to discuss this variance of IPC, which I like to call Intelligent Process Control. We'll discuss a little bit of the basic programming of how to implement it, and then we'll just have a brief summary. To start with, let's discuss how IPC, or Intelligent Pump Control, which is how it's known in the ACH 580 manuals today, works. The concept of IPC is that there's no building automation system. And what we have is we have one drive per motor, and we have at least 2 drives and 2 motors in the system. IPC can be used with up to 8 drive and motor combinations. The way it works is all the drives are connected together via an RS-45 link, where the drives will talk to each other via an embedded protocol. Now, the drives then will be hooked up to a transducer. Now, in pumping applications, traditionally that's either water pressure or water flow, and that signal will be fed back to each of the drives. The drives then will vary the speed of the motor to maintain a constant pressure or flow in the system. Usually, there's also redundancy in a pumping application. So, for example, let's say you had 3 pumps, only 2 may ever need to run at one time, and 1 will be in standby. What will happen is with IPC is the drives will alternate each other, also making sure that there's even wear time on each of the motors and pumps, so you don't have any impeller, for example, seize up over time. And if any one drive motor combination were to go down on a fault, because you have a backup there in a 3-pump system, if one motor fails, the other drive will automatically kick online via the communication over that RS-45 link and maintain either constant pressure or constant flow in the system. Now, besides booster pump applications that I previously talked about, another application that IPC can be used on in the traditional sense with the transducer is on a cooling tower system, where I have one drive and motor, each connected to the fan in a cooling tower. In this situation, instead of monitoring pressure or flow, I'm going to measure discharge water temperature. And that's why I like to call this intelligent process control instead of intelligent pump control, because there are other applications for IPC. When I talk about IPC, I always want to cover what does that look like in terms of implementation of wiring between drives and what signals are going where, just so everyone better understands what I'm talking about. So here on the image on the right, I have a traditional IPC implementation where each drive is connected, as you can see, to an individual motor. And each drive, to start with, is connected to a transducer. In this case, this transducer is a pressure transducer, providing feedback signal to each drive. Each drive also has to have its own independent run command. Sometimes this run command is actually just a jumper wire on the drive, or it could be an independent signal. Sometimes maybe even simple like a switch on a piece of machinery that would just give the drive a run command, allowing it to run if needed in the system. And then the other critical component of intelligent pumping control system, or IPC system, where it's using a transducer, is the communication, the drive-to-drive link communication, which is shown here. This is an RS-45 communication link. I did not show in this example any safety circuits connected to the drive, but that very well could be in play here. If, for example, on an air handler, you had a high static safety, you'd want to make sure the high static safety is wired to each one of the drives independently, also like the run command is. Here I just want to show real quick, each drive, you always want to have independent interlocks and permissives as needed connected to each drive. So if you have a common safety circuit in the system, you want to make sure that's connected to each of the drives. And then permissive circuits that could, for example, be used to open a damper, well, that you'll want to make sure is connected to each respective drive accordingly. So each drive could either open a common damper or maybe independent dampers, for example. Now, if you look at the schematic on the right, it looks almost identical to what we just saw in the previous diagram, except in the upper left corner, instead of there being a pressure transducer, I'm showing in this case a PLC. Now, this could also just be known as a building automation controller, or it could even be a simpler device like a local controller. In any case, in this setup, I'm sending it, for example, a 0 to 10 or 4 to 20 milliamp signal to each drive, representing a linear 0 to 60 hertz. It could also be greater than 60 hertz for applications that require overspeeding, for example, up to, let's say, 90 hertz. Now, this system provides you is if I, for example, need 3 out of 4 drives always to be running. With the new implementation of IPC, I still have automatic system redundancy. So if my simple local controller cannot provide me this automatic system redundancy, it just provides a simple speed signal to each drive, and I need 3 out of 4 drives always running. If any one of these drive motor combinations were to go down on a fault, the other drive will automatically kick on and pick up the slack. Now, many of you are probably thinking, hey, this is a great new use of the IPC and the ACH 580 drive, but when would I really need to use this? As most systems have a full-blown building automation system that manages redundancy automatically for all the fans and pumps, for example, in a hospital or data center. Well, there are some systems where maybe it's just a very simple local controller that doesn't have the ability or is not set up to monitor the fault status of each drive in, for example, a fan array, the image on the right. So the use of IPC will allow for this automatic backup system redundancy. Now, in this scenario, for example, you determine the system, I need to run, for example, 5 out of 6 fans in a fan array, okay? So when any one of those 5 fans and drive motor combinations that's running fails, the other 6th or backup drive motor combination will automatically come online with this use of Intelligent Process Control, or IPC. Now, what is required in a fan application system is to make sure that you do have backdraft dampers on each of the motors, because otherwise you'll have circulating air flowing. These could be simple barometric or gravity-fed dampers, or maybe it's a larger parallel fan system where you have motorized dampers. If you have motorized dampers, you can use advanced damper control logic in conjunction with IPC in the drive so that the motorized damper will open first before the motor starts spinning, or actually with advanced damper control, we can even do what's called a pre-puff. So we'll spin the motor up to a minimum speed, and then once the damper fully opens, the drive will release to its full speed that's being commanded from the local controller. In the previous slide, I was kind of referring to, for example, supply fans, or maybe large return fans. Well, another application related to fans could also be just simple exhaust, relief, or fume hood fans, for example, where this feature could be implemented. These could be implemented, for example, in a science lab for fume hoods. Maybe there's a simple manufacturing process where you need exhaust fans to get rid of some gases in a manufacturing process. That's where a great use of this feature is. You have automatic redundancy. I don't want to have to all of a sudden implement maybe, for example, a controller that's going to have to be integrated and tied to each drive's status to monitor fault status, and then have to write up the logic in the controller to command each drive when to turn on and when not to turn on. The IPC in the drive, the Intelligent Process Control in the drive, will manage that automatically for you. So it's a great way to save money if just needing to implement a very simple exhaust relief or fume hood fan application. Pump systems are another great use for this new feature. For example, you could have a multi-drive, multi-motor pump skid. Maybe it's for potable water, or maybe it's a pressure washing system at a food plant. Another use is, let's say, at a water park. It could be for the filtering and moving of the water in pools, or maybe it's at a water park, it's the water being pumped up for the water slide. The great benefit of this feature is, for example, let's say, for example, I know at a water park slides, I just need to run the drives at 40 hertz. Maybe it's even programmed in the drive at a fixed speed, preset in the drive. But I do have redundancy automatically in the water park, but the drives aren't tied together. There's no control system. So this system, by using IPC here in this system, if one drive motor were to fail, the other one comes online. So if someone's standing at the top of the water slide about to go down, and all of a sudden one drive motor fails, they're all of a sudden stuck like the water slide just broke, can't go down it. Nope, automatically the other one kicks online, and they may not even notice that there's a change in water flow at the top of the water slide, and every kid that's been standing in line to go down that water slide will get their chance to go down it. Now, for those of you that are sold on this new feature and want to know, how do I set up my drives to use it? Well, I want to discuss that with you at a very high level here in the rest of this presentation. I'm not going to go into extreme detail of every parameter setting, as that'll become too exhaustive, and I will provide other information about either in written text form or other AV presentations of how to set up this feature on the drive in more detail. But at a high level, I recommend starting by using primary settings to implement the IPC. This will help synchronize some drive parameter settings and get the drive-to-drive link communicating. I don't recommend in primary settings, though, setting up the feedback signal and set point feature in primary settings for IPC. We'll discuss that in the following slide under normal programming. But in primary settings, while setting up IPC, a couple important things here. First off, on the lower middle slide screenshot there, I have the always run at least and never run more than settings. These two settings have to be set to the same number in your system, okay? In my system, I had a total number of 2 pumps or 2 drives, okay? I'm only going to ever want to run more on one of them at a time. So I'm going to set each always run and never run more than 1. Now, for example, let's say you had 4 drives, 4 motors in your system, and you want to run 3 always at the same time. You're going to then set always run at least to 3 and never run more than to 3. That gives you that 1 drive motor combination as your backup if you have a 4 drive, 4 motor system, for example. The next item is, how do I get the proper units on the screen? By default, Hertz or RPM, if you're running in vector mode, are not default units in the under PI control for feedback signal units. So there's a way of setting up custom units and entering HZ or RPM into the drive. This can be done either through the synchronization setting wizard, which is part of the IPC setup, or if you go back to basic primary settings, the clock region display option, edit text and PID unit, you can then manually enter in HZ for if you're operating in scalar mode, which is default, or if you're operating in the vector control mode, you could enter in the letters RPM, for example. Now I want to discuss with you how to program the PID parameters in group 40 so the drive acts as a speed follower. To do this, I recommend going into the main programming menu, the complete list, and navigate to group 40. Now, a couple important parameters that are not obvious of how to set up the drive as a speed follower. The first one is parameter 4008. Okay, this one we want to set to, using the other feature, the output frequency of the drive, which is parameter 01.06. The next parameter we need to set is a set point source. In this case, I used AI1 scaled. If you have your analog signal set to example hooked up to terminal AI2 on the drive, you set this to AI2 scaled. You'll then also just leave or adjust as necessary group 12 parameters. So your 4 to 20 or 0 to 10 volt signal is scaled between 0 and 60 hertz or 0 and 90 hertz, for example, if you're running above base speed. Another important parameter is parameter 4031. This is important to be set to not inverted. If you don't set it to not inverted, the drive will not operate properly as a speed follower. The next two parameters, the gain and integration time. The drive actually, as I've stated, is running the PID loop. So we do need to have a value in the gain greater than 0 and a value greater than 0 in integration time is my recommendation. I have a gain of 2 and an integration time of 5 in this example, my setup, and that I did in testing. The drive's normal accel decel settings that are set up in group 28 in scalar mode will dictate the main ramp up and ramp down rate of the drive. But we do need to have a value greater than 0 in the gain, and integration time, I recommend maybe, for example, a value of 5, but in each scenario, you can always tweak and adjust these as necessary. And last, set user 1 units. I have this set to user text because I need hertz on the screen, so I set this to user text. Now in group 76, I just want to cover a few settings just to make sure they are set correctly if you're in the complete parameter list. Most of these settings should automatically already be set to the following settings that you see here by default because you use primary settings to set up IPC already. The first parameter I just want to cover, the first two are 7626 and 7627. Just verify again that these two are set to the same value, as these are the min and max number of motors that are allowed to be run. So, for example, if you have a 6-fan system or 6-drive motor system and you only want 5 to run at a time or 4 to run at a time, these will either be set both to 5 or maybe they'll be set both to quantity 4. The next parameter I want to discuss is 7670. This is how the system will automatically rotate the drive motor combinations. This is especially important in a pumping system where you want to make sure maybe you don't damage a pump by having a seal dry out because the pump hasn't been running so many hours or so many days. So my recommendation is just leaving the default set to even wear, and then just adjusting as necessary the number of hours before rotation. The last parameter here is 7673. It's very important that you leave this at 100%. If you don't leave it at 100%, the auto rotation will not occur. So make sure this is left at 100%. Now, some of you may be thinking, what happens to the system if my external 0 to 10 or 4 to 20 signal, for example, from the PLC or local controller is lost? What will the drives do in this IPC system? And how can I program the drives so that they don't just stop running and do nothing? That's what I'm covering in this slide here. What I've done is giving you an example set of programming that you can use as supervisories in group 32 to monitor the analog input signal. And for example, in this setup here, I'm doing a 4 to 20 signal. So if my signal goes below 4 milliamps, the supervisory circuit will trigger a constant frequency programmed in group 28 to allow the number of drives required to keep running. What's important to understand, and a nice feature in this setup, is that if, for example, I have 5 drive motor combinations running out of 6, the IPC will still manage to make sure I only have maximum of 5 running if I lose my analog signal to all the drives. Okay, so the IPC is still maintaining proper number of drives that are allowed to run at any one time. And if any one drive were to fail, go out on a fault, for example, a motor earth fault, another drive motor combination will automatically come online running at the same constant frequency that we've programmed in the drive because our remote analog signal has been lost. Now let me just recap what we just learned. We can use the IPC functionality in the ABB drive not only for the use of system redundancy where you have one drive, one motor with a pressure transducer or some sort of transducer feedback, but we can also set it up and use it with an analog speed signal or maybe a fixed speed signal that's pre-programmed in the drive. The use of the IPC will provide the same great automatic system redundancy that you've learned to expect when you set it up with a transducer. Applications for this can be fan arrays, exhaust fans, relief fans I discussed earlier. Also for pump applications, you could have a booster pump skid, or I mentioned an example of maybe some pumps at a water park. And how do I program the drive for this functionality? Well, I first recommend using primary settings to initialize the IPC setup in the drive so the drives are talking together. And then I discuss going into the complete parameter list in the drive to program some specific parameters such as the feedback and set point in group 40 of the drive. Further documentation and information about how to program all the parameters in the drive for the setup will come at a future time. If you have any questions though, before that information is available, please reach out to your local ABB representative and they'll be able to assist you.